Today, we're looking at a totally fascinating intersection where highly abstract, pure mathematics crashes headfirst into physical, heavy-duty engineering. We're going to explore industrial polymer manufacturing, and we'll see exactly how the linear algebra you might remember from school serves as the literal safety net preventing massive industrial machines from just completely tearing themselves apart. Okay, let's dive into this. It's a pretty provocative question, right? When you think of a factory floor churning out things like 3D printing filament or plastic pipes, you probably picture grinding gears, massive hoppers of raw materials, and just intense glowing heat. You definitely don't picture a mathematician furiously solving a matrix equation on a whiteboard. But as you'll see today, understanding a complex system of linear algebraic equations is the exact literal barrier between an incredibly smooth, successful manufacturing run and an absolute catastrophic failure on the factory floor. Section 1, the polymer temperature problem. So, in the high-stakes manufacturing of semi-crystalline engineering polymers, like Linear Low-Density Polyethylene, or LLDPE for short, process stability depends on a highly exact, spatially varying temperature profile, and this profile is distributed along the length of a heavy, solid tool steel processing barrel. Temperature control here isn't just a suggestion, it must be absolutely perfect. Think of it as the ultimate Goldilocks problem. If the temperature drops even slightly below the polymer's crystalline melting point, the plastic just refuses to flow. This leads to immediate clogging, severe pressure spikes, and ultimately catastrophic structural failure where the machine's drive gears literally shatter under the sheer strain. But if the machine runs too hot, well, we face a completely different disaster. The polymer chains undergo rapid thermal degradation, which we call chain scission. This introduces these tiny gaseous microvoids into the plastic, which entirely ruins the finished material's mechanical strength and its look. The margin for error here is razor thin. Moving right along to Section 2, 3 zones of heat. So how do engineers actually manage this balancing act? Well, they use an extruder machine, which physically heats the raw material in distinct, tightly controlled stages. See, we can't just blast the plastic with a single giant furnace. We literally have to walk the material through a very specific thermal journey across 3 distinct physical stages as it moves from the hopper to the shaping die. First up is the feed zone, which preheats the solid thermoplastic pellets as they drop in. Next, we hit the transition zone. This is the real heavy lifter. It compresses, shears, and actually melts the polymer using both electrical heat and mechanical energy. Finally, we reach the metering zone. This last stage homogenizes the melted plastic, making sure there's uniform head pressure before pushing the molten polymer out. Which brings us to Section 3, the thermal crosstalk threat. Now, on paper, hitting those 3 distinct target temperatures sounds simple enough, right? But here is the massive physical twist. These 3 heating zones do not exist in isolation. They share a continuous high-strength tool steel barrel, and that introduces our core thermodynamic villain for today, thermal crosstalk. Imagine you have a building with 3 rooms, and you want each room to be a drastically different temperature, but the walls separating them are made of thin, solid steel. If you blast the furnace in the middle room, that heat is naturally going to bleed right through those walls into the adjacent rooms. This is exactly what happens in our extruder barrel. Pumping thermal power into the feed zone naturally bleeds multi-directional heat into the transition and metering zones. What's really interesting about this slide is the profound irony of the engineering itself. The very material the extruder barrel is made of, this continuous high-strength tool steel, is specifically chosen because it can withstand the absolutely incredible mechanical pressures of industrial manufacturing. But its excellent conductive properties create our biggest thermodynamic headache. The heat conducts fluidly down its geometric length. We absolutely need that physical strength, but that same strength guarantees our heat is going to leak everywhere.
Section 4, a recipe for disaster.
So what actually happens if human intuition just ignores this crosstalk? What if an operator tries to heat each zone as if the others don't even exist? Well, if operators naively apply power, treating each heater as an independent, single-input, single-output system, a SISO system, they calculate the power needed in total isolation. According to our source data, this simplistic, decoupled logic tells the controller to apply an isolated input power vector of exactly 360 watts to the feed zone, 350 watts to the transition zone, and 328.5 watts to the metering zone. And this brilliantly illustrates the horrific consequence of that assumption. When we drive the physical plant with these uncoupled values, all that unmodeled heat leakage from the continuous steel barrel triggers severe constructive thermal interference. I mean, look at this. The temperatures absolutely skyrocket past their targets. The feed zone hits 248.9 degrees Celsius, the transition zone shoots to 312.3 degrees, and the metering zone hits 293.3 degrees. It's a total mess. I want to emphasize this terrifying central temperature right here, 312.3 degrees Celsius in the transition zone. For our LLDPE plastic, exceeding 300 degrees Celsius is completely fatal to the material. At this extreme temperature, we trigger that rapid polymer chain scission we talked about earlier. The material's shear strength just collapses, those gaseous microvoids form. The final product is completely ruined, both aesthetically and mechanically. The decoupled assumption is a complete, utter failure. All right, time for the fix. Section 5. Matrix math saves the day. To actually rescue this operation, we have to totally abandon that decoupled assumption and outsmart the heat bleed using a multi-input, multi-output, or MIMO thermal model. We do this by turning to Fourier's law of heat conduction and expressing it through linear algebra. Instead of 3 isolated formulas, we use a single integrated interaction framework, a 3x3 linear algebraic matrix, represented by the elegant equation T equals A times Q. T represents our target temperatures, Q is our required heater power, and A is our matrix of thermal influence coefficients. This beautiful piece of math maps out not just the dominant localized heating on the primary diagonal, but crucially, it captures those minor off-diagonal elements that represent the multi-directional heat bleeding across adjacent zones. By constructing this matrix and using a technique called Gauss-Jordan row elimination to invert it, our systems can calculate the exact, real-world wattage needed to perfectly balance the thermodynamic bleed. Let's look at the solved input power. To hit exactly 180 degrees in the feed zone, 210 degrees in transition, and 230 degrees in metering, the math tells us we need exactly 268.39 watts, 215.02 watts, and 270.99 watts respectively. Notice how the metering zone requires 270.99 watts to hit 230 degrees, which is barely more power than the much cooler feed zone requires. Why? Because the math perfectly accounts for the thermodynamic assistance the metering zone is receiving from heat bleeding over from the central transition zone. It's perfectly balanced. And what confirms that this mathematical model is physically sound is that all of our solved wattages are positive, non-zero real numbers. This is an absolutely vital sanity check. Remember, standard industrial resistance bands can only add heat. If the math had spit out a negative wattage, it would imply the system needs impossible active refrigeration to work. But because our required power is strictly greater than zero, the matrix solution perfectly respects the fundamental, real-world boundaries of the hardware. So to sum this all up, our two approaches are just worlds apart. On the left, ignoring the heat bleed with a naive, decoupled CISO approach practically guarantees severe thermal interference, ruined material, and potential machine failure. But on the right, by leaning into the complexity with a coupled MIMO matrix model, we achieve exact, uniform processing. We don't magically stop the heat bleed. We just mathematically untangle it so the machinery works in perfect harmony. Honestly, it's incredible to see how a concept so often confined to university whiteboards is actively saving millions of dollars on factory floors right now. It really makes you wonder what other hidden, invisible disasters in our modern physical world are just waiting to be completely averted simply by applying the right mathematical model. Keep that in mind next time you hold any precision-engineered product. Thank you so much for joining me for this explainer. Keep exploring and stay curious.